95%, not 90%, 95% of all column in building are tight column. Anyway, according to ACI, the design axial load capacity of tight column equal to 0.8 times phi time big brackets 0.85 FC prime area gross minus area steel plus F yield times area steel AG area gross A steel area steel of longitudinal bars FC prime. I repeated this one. Anyway, phi, which is a factor for capacity factor 0.65 for tight column. So from a structural analysis, this girder is supported what? We covered this point before in structural analysis, I believe. Your load is coming to slab, that's right?
Mm-hmm.
Your slab supported by beams. Your beams supported by columns. Your columns supported by footing. That's right? From structural analysis point of view, your beam, which is supporting your slab, and your slab supporting live load and covering and all of this stuff, this beam has a reaction at each column. That's right? This reaction on your column make compression. This reaction must be smaller than or equal the design axial force of your column. This way. With your design philosophy, P ultimate must be smaller than or equal phi Pn. So, from structural analysis or reason, we can figure out what is the reaction on your column. From your design, we can figure out what is the design axial capacity. Then we can make comparison. But I need to say something. What is the mean of area gross? Area gross is the total area for this shape, including everything inside. So we need to subtract what is the area of steel, because this area of steel does not count or does not count it as concrete. So we need to remove this one. Then plus what is the contribution of your steel, F yield times area steel. Let's see some examples, but before examples, we have something we need to respect.
Phi?
Me.
Oh.
No, phi equal 0.65.
Don't listen to Elmer.
These notes are very important. Please keep it in your mind and write it important, because you will need them in your exam, in your design for general exam. Percentage of longitudinal steel may not be less than 1% nor more than 8%. Anybody can understand anything from this sentence? Yeah? We learned something a little bit like this before. Do you remember rho required in your beam? If you multiply rho times P times depth, you can get area steel required. What you did next? Check that area steel required from calculation greater than area steel minimum smaller than area steel maximum. Do you remember? The same here. Your column has steel reinforcement with area steel. If you divide your area steel by area concrete, you can get a percent. This percent must be more than 1% and smaller than 8%. So your area steel divide area concrete as a percentage greater than 1% and smaller than 8%. So we can say, hey, the minimum reinforcement ratio 1%. The maximum reinforcement ratio in your column 8%. Your steel reinforcement in column must be in between. Percentage why? Because we have a calculation area steel related to what is the area concrete as a percentage.
Dr. Amen?
Yeah.
I have a question. I understand that, that our column is going to be under compression for the majority of what we're designing. So why are we interested in putting rebar or because of torsion and shear?
Good question. Can you watch this column? If this column is concrete only without any reinforcement, it must be 3 times this size. Like this, from here to here. So we are trying what's this value?
FU.
50? That's right? For concrete in compression. What's this value?
4,000.
4. We are talking about KSI. 4. So steel is stronger than concrete in compression. How many times? Wow. So a little bit of steel can be equivalent for a huge amount of concrete. So if you did not put any reinforcement in your column, your size of column will be maybe 5 times or 6 times or 10 times. It will reduce your architectural design. Okay, you got it? So we put steel reinforcement to reduce the dimension of your column. For high-rise building, the common column used something like this. We have a huge reaction because you are supporting maybe 100 floors. So we have a huge reaction in your column. If you design your column for concrete only, no way. Maybe you need 1 column like this building, 1 column. If you put steel reinforcement like this, maybe your column will be a quarter of this building. But if you put steel members like this, we reduced our column to be something like this room. You got it? So how much steel reinforcement means how much you reduce the cross section of your column. Okay, at least 4, according to ACI, at least 4 longitudinal bars must be used within the rectangular or circular ties column. So if you have a column, at least you have to put how many bars? 4 or more. You cannot be 3 bars or 2 bars, no way. At least 6 longitudinal bars must be used if your column is a spiral. If your column is a spiral, no, at least 6 bars. the practical minimum column dimension is about 8 to 10 inch. We will use all of this information in your problems, in your design. We have 2 dimensions of your column. Maybe we can call it B and H. The minimum dimension of your column 8 to 10 inch. So we can make it 10 inch. No smaller than 10 inch. 10 times 10. 10 times 10. Or 8 times 8, whatever. For tight column with number 10 and smaller, if your steel reinforcement here, number 10 or smaller, the minimum size of tie is number 3. These ties must be number 3. If your longitudinal column larger than number 10, number 11, 12, or whatever, the minimum size of your tie must be number 4. If your bars, longitudinal bars, greater than number 10. Very huge diameter of your bars. For tight column, the maximum ties spacing this spacing between stirrups, between ties. The maximum spacing may be the smaller of 48 tie bar diameter. What is the diameter of the tie? 48 times. 16 times longitudinal bar diameter, or the least lateral column dimension. The least one, or 16 times diameter of longitudinal bar, or 48 times the diameter of your stirrup. This is the maximum spacing between ties. The most important thing we need to learn from this slide, what is the minimum percentage of your steel, what is the maximum. Your steel must be in between. The second thing we need to understand, to learn, to remember, the minimum dimension of your column, 8 to 10 inch. These are the 2 most important information. Let's do first example. But before first example, one more information. What's going on? Yeah, more details about concrete design. Can you watch the spacing between this bar and this bar? Spacing, clear spacing from this edge to this edge. If your clear distance between this bar and this bar equal 6 inch or less, I can put this bar without any additional tie. But if this distance greater than 6 inch, no. This bar and this bar need 1 leg additional to your tie. You got it?
Is that center to center or?
No, face to face.
Wait.
As you see here,
Yeah.
face to face. Okay? So if the distance between, so all of these details must be respected in your design. This distance, 6 inch or smaller, I don't need to add more legs in your tie to support the intermediate bars. The corner bars, that's fine, because we have leg here and leg here. 2 legs. But for the intermediate bar, this bar, for example, and this distance greater than 6, this bar must be supported by 2 legs. Actually, we have 1 leg here, so we need to add another leg here. If this distance equals 6 or smaller, we don't need additional leg. That's fine. Okay? Okay, I think it's time for example. First example. It's very simple example. Column is very simple. For the short column shown blue, FC prime equal 4,000, F yield equal 60,000. What is most nearly the ultimate axial strength? Phi Pn. So I think your phi Pn equal what? Phi or 0.8, phi 0.85 FC prime times area gross minus area steel plus F yield times area steel. That's right? Go ahead and put your number. That's all. Go ahead and put your number. Phi 0.65 because your column is tight column. FC prime 4,000. Area gross. What is the total area of your cross section? We have a column here, 16 inch times 16 inch. So the total gross area of your column, 16 times 16. What is the area steel? Actually, your longitudinal reinforcement, number 9. Open your table. For number 9 bar, what is the area steel? 1 inch? I think 1 inch square. But we have 8 bars. So your area steel will be 8 bar time area of 1 bar, 1 inch square. F yield 60,000. Area steel 8 bar time 1. That's all. You can figure out what is the